Hello, my name is Dr. Kenneth Watanabe, and today I will go over the definitive proof of the twin prime conjecture. The twin prime conjecture states that there are an infinite number of pairs of prime numbers, P1, P2, such that P1 plus 2 equals P2. This conjecture was first proposed in 1849 when de Polignac made the more general conjecture that for every natural number k, there are infinitely many prime pairs, P1, P2, such that P1 plus k equals P2. And the twin prime conjecture is the case where k is 2. Since then, the conjecture has remained largely unproven until Chinese mathematician Yitan Zhang in April 2013 proved that there are infinitely many prime pairs, P1, P2, such that P1 plus n equals P2, where n is less than 70 million. And here is a link to his paper. I tried reading it, but it is a little bit outside of my capabilities. All right, so here in this presentation, we'll prove a more constrictive conjecture that there is at least one twin prime pair, P1, P and P plus 2, such that P is in between P sub I squared and P sub I plus 1 squared. Okay, and so for example, if P sub I equals 3 and P sub I plus 1 equals 5, there is at least one twin prime between 9 and 25. And in fact, there are two, 1113 and 1719. Since it was proven that there are an infinite number of prime numbers by Euclid in 300 BC, this will prove that there is an infinite number of twin prime pairs. All right, so first thing I did was I wrote a little Python script to count the number of twin primes less than n for values of n all the way up to 50,000. And you can see we have a nice curve that looks like it goes up indefinitely. So it looks like there's very likely an infinite number of twin primes. Of course, a graph is not a proof. We don't know whether the graph will eventually just flatten out as n gets larger. Before I actually get into the proof, let's go over a few functions that must be defined. P sub n equals a set of pairs xy such that x plus 2 equals y, and y is less than or equal to n. Vertical bars around P sub n would equal the number of pairs in the set P of n. And in this case, P of n will be n minus 3 over 2. Lambda sub x is the largest prime number less than or equal to x. K sub n is the number of pairs xy in P sub n where either the x or y is a composite integer. W of n is the fraction of pairs in P sub n where both the x and the y are prime. And pi sub 2 of n is the number of twin pairs xy such that x plus 2 equals y, and y is less than or equal to n. So this, we can also call this the twin prime counting function. Right? So to solve this conjecture, I use the sieve of Eratosthenes. This is an ancient algorithm to find the prime numbers less than n. So starting with a list of positive integers greater than 1. So here's a list of positive integers greater than 1, and we have an endpoint here of 27. And what we do is we take the first number in the list, that's a 2, and we eliminate everything divisible by 2, all the way up to 27, the endpoint. Then we take the next number in the list that hasn't been eliminated. In this case, that would be 3. And then we eliminate everything divisible by 3. Then we take the next number that has not been eliminated, that would be 5. And we eliminate everything divisible by 5. And we don't have to go any further than that. We don't have to check for numbers divisible by 7. I mean, there are numbers here that are divisible by 7, like 14 and 21. But those have already been eliminated because 14 is divisible by 2 and 21 is divisible by 3. The next number that would be divisible by 7 that has not already been eliminated would be 49. But 49 is greater than the endpoint here, which is 27. Okay, so we only need to go up to the square root of this endpoint, which is about 5. Okay, and the numbers that have not been eliminated are prime numbers. So in this proof, what I do is I apply the proof to pairs of integers. Okay, so for example, for n equals 59, what I do is I arrange pairs 3, 5, 5, 7, 7, 9, all the way up to 57, 59. Okay, and I eliminate all numbers, all pairs where either the x or the y coordinate is divisible by 3. So excluding 3, 5. Okay, so that is, so we have 7, 9, 9, 11. Those have a coordinate. So the 9 is divisible by 3. 13, 15, and 15, 17. 15 is divisible by 3. 19, 21, 21, 23, etc. Okay, and note, every group of 3 pairs, we are eliminating two of them. Okay. So as n gets very large, the number of pairs divisible by 3 approaches 2/3 p sub n. So we call that k sub 3 of n. That's the number of pairs divisible by 3. If we subtract that from the total number of pairs, that will give us the number of pairs that are not divisible by 3. We'll call that pi sub 3 of n. All right. So in this case, p sub n minus k sub 3 of n is 1/3 p sub n. Okay. Next, we eliminate all the pairs where the x or y component is divisible by 5, excluding 5, 7. Okay, so that will be 13, 15, and 15, 17, because 15 is divided by 5. 23, 25, 25, 27, 33, 35, 35, 37. So as you can see, every 5 pairs, we are eliminating 2. Okay, so for large n, the number of pairs divisible by 5 is about 2/5 of p sub n. But if you notice, about 2/3 of these have already been eliminated. We're only eliminating 1/3 of the numbers. So for very large n, the amount of pairs divisible by 5 and not divisible by 3 approaches this here, 1/3 times 2/5 times p sub n. Okay. To find the number of pairs that are not divisible by either 3 or 5, we can subtract k sub 5 of n from pi sub 3 of n, and that will give us 1/3 times 3/5 times p sub n. Okay, so those are the number of pairs not divisible by 3 or 5. Okay, and then we continue with 7. We eliminate all the pairs that are divisible by 7, so that'll be 21, 23. That'll be 19, 21, and 21, 23. 33, 35, and 35, 37. 47, 49, and 49, 51. So again, every 7 pairs. So if we look at groups of 7, 2 out of every 7, uh, the x or the y coordinate is divisible by 7. And some of these have already been eliminated. So if you want to only exclude those that are divisible by 7 that have not already been eliminated, k sub 7 of n equals 1/3 times 3/5 times 2/7 times p sub n. And if we subtract that from pi sub 5 of n, this gives us 1/3 times 3/5 times 5/7 times p sub n. And that will be all the pairs that are not divisible by 3 or 5 or 7. And we'll call that pi sub 7 of n. Okay, and in this case, we only need to go up to 7 because the endpoint here is 59. The next higher prime number is 11, and 11 squared is greater than 59. So we only have to go up to the square root, the largest prime number less than the square root of 59, and that will be 7. All right, so all the remaining pairs that have not been eliminated, those are twin primes. All right, so for large n, the number of twin prime pairs can be approximated by the following equation. We'll use a capital pi sub 2, and we'll put a star here to indicate that this is an approximation. So capital pi sub 2 star of n is p sub n times the product of p equals 3 to the up to the square root of n of p minus 2 over p. Okay, where this lambda of the square root of n is the largest prime number less than the square root of n, and this product is over prime numbers. Okay, and this part of the equation here, this product, we can call this the w function. So w of n. So this equation simplifies to pi sub 2 star of n equals the number of pairs p sub n times w sub n. Okay, so now that we have an approximation, the next thing I did was I plotted my approximation to the actual number of twin primes less than or equal to n. Okay, so here's the plot. The blue line here is the actual number of twin primes less than n, pi sub 2 of n, the twin prime counting function. And this red line here is my approximation, pi sub 2 star of n. And for n less than 5,000, my approximation, this red line here, is a little bit less than the actual twin prime counting function. But if for larger n, here on the right we have a graph of n up to 50,000, and you can see as n gets large, the approximation approaches the actual twin prime counting number, and the curves, they line up on top of each other. All right. If you look closely at the curve on the left, you can see this. My approximation is quite jagged. You can see it has a sawtooth shaped. And the reason for that is because the w function only changes when n crosses the value of a prime number squared. So here is a depiction of the points on the graph. We got when n is p sub I squared minus 2. When n becomes p sub I squared, the w function, a new term to the w function is added. This lambda sub square root of n changes and another term is multiplied with w sub n, and that causes a drop. And then between points B and C on this chart, where n goes from p sub I squared to p sub I plus 1 squared minus 2, the curve slopes up at a steady rate proportional to the number of pairs, p sub n. Because in the range between B to C, w sub n is basically a constant. When n reaches p sub I plus 1 squared, the w function changes again, and then we have another drop. Okay, so we know that points between the region between points B and C, the curve slopes upward with a slope equal to the number of pairs. And if we can prove that point D is always greater than point B, then this proves that that the pi sub 2 star of n function goes up indefinitely, and this will prove there are an infinite number of twin primes. All right. So if we examine the w function, we can get the w function of p sub I plus 1 squared in terms of p sub I squared. Okay, so w of p sub I plus 1 squared equals p sub I plus 1 minus 2 over p sub I plus 1 times w of p sub I squared. Okay, let's define this function delta pi sub 2 star of p sub I equal to pi sub 2 star of p sub I plus 1 squared minus pi sub 2 star of p sub I squared. Okay, so if we substitute the values here, we get delta pi sub 2 star of p sub I equals the number of pairs of p sub I plus 1 squared times w of p sub I plus 1 squared minus the number of pairs of p sub I squared times w of p sub I squared. And since w of p sub I plus 1 squared can be put in terms of w of p sub I squared, we can substitute this term here for this term, here, and then we factor out the w of p sub I squared, and we replace this number, put this number of pairs in terms of p sub I and p sub I plus 1, and we get this result. W of p sub I squared over 2 equals times this mess here equals delta pi sub 2 star of p sub I. Okay. Now, if we can prove that this term here is greater than 1, that will prove that there is at least one twin prime between points D and point B on this curve here. Okay, so to minimize this here, we have to minimize what p sub I plus 1 is. Okay, and the lowest value that p sub I plus 1 could be is p sub I plus 2. Okay, that's the smallest value p sub I plus 1 can be. Okay, is p sub I plus 2. So we plug in p sub I plus 2, this term, in for this p sub I plus 1, and then we simplify and we get the minimum value of delta pi sub 2 star of p sub I is w of p sub I squared over 2 times 2 p sub I plus 6 over p sub I plus 2. Okay, and if we ignore this thing here, we can say that delta pi sub 2 star of p sub I is greater than p sub I times w of p sub I squared. Okay, so these 2's will cancel out. And we know that delta pi sub 2 star p sub I is greater than p sub I, w of p sub I squared. So this represents the lower limit, the lower bound on delta pi sub 2 of p sub I squared. Okay, so what I did was, for values of n equal to a prime number squared, I plotted the actual number of twin primes between p sub I squared and p sub I plus 1 squared, and I compared it to my delta pi sub 2 star of n, okay, and which is this orange line here. And you can see that this orange line is a lower bound for the actual number of twin primes between p sub I squared and p sub I plus 1 squared. Okay, so if I can prove that delta pi sub 2 star of p sub I is greater than 1 for all p sub I, then this will prove that there are an infinite number of twin primes. Okay, so to prove that delta pi sub 2 star of p sub I is greater than 1, we'll use proof by induction. So the base case is when p sub I is 3. So we plug in 3 into this delta pi sub 2 star of 3, and we get 3 times w of 3 squared. And this is 3 times 1/3, which is 1. Okay, so we know that there's at least one twin prime between 3 squared and 5 squared. Okay, next we'll assume that delta pi sub 2 star of p sub I is greater than 1, and prove that delta pi sub 2 star of p sub I plus 1 is greater than or equal to 1. Okay, so delta pi sub 2 star of p sub I plus 1 is p sub I plus 1 times w of p sub I plus 1 squared. And we can get, we know that w of p sub I plus 1 squared can be put in terms of w of p sub I squared. Okay, and these p sub I plus 1s will cancel out, and we'll end up with delta pi sub 2 star p sub I plus 1 equals p of p sub I plus 1 squared times w of p sub I squared. And then we multiply and divide by p sub I, and we get this p sub I plus 1 minus 2 over p sub I times p sub I times w of p sub I squared. And this term here is equal to delta pi sub 2 star of p sub I times p sub I plus 1 minus 2 over p sub I. And we assumed that this is greater than 1, and p sub I plus 1 minus 2 over p sub I is greater than or equal to 1. So this proves that there is at least one twin prime between p sub I squared and p sub I plus 1 squared. Okay, so this proves that there is an infinite number of twin primes. Okay, so I took this proof to a professor and asked him about it, and there's just one little problem. Okay, and that problem is I've proven that this pi sub 2 star of n goes up indefinitely. But the problem is pi sub 2 star of n is not equal to the twin prime counting function. Okay, so to prove that there are an infinite number of twin primes, I have to prove that the difference between my estimation, my pi sub 2 star of n, and the actual twin prime counting function is small. I have to prove that the error, the difference between my derivation and the actual twin prime counting function is small. All right, so to do that, I have to look at how I derived my twin prime counting function. And what I did was the actual number of pairs divisible by 3, I estimated to be 2/3 p sub n. Okay, so what I did was I have a table here of what 2/3 p sub n is for various values of p sub n, and in this column here I have the actual number of twin primes, actual number of pairs that are divisible by n, and I compared them, and the maximal difference is 1 1/3. Okay, and this occurs at when p sub n is 2, 5, 8, 11, etc., and it is 1.3. Then I did the same for 5. The number of pairs divisible by 5, I estimated to be 2/5 p sub n, and I compare that to the actual number of pairs divisible by 5, and this turns out to be, the maximum turns out to be 2 at when p sub n is a multiple of 5, so at 5, 10, 15, 20, the maximum error is 2. And then I did the same for 7. I estimated that 2/7 of the pairs are divisible by 7, and I compared that to the actual number of pairs divisible by 7, and the maximal difference occurs at when number of pairs is 8 plus some multiple of 7, so 8, 15, 22, etc. And that maximum is 2.285714. Okay, and I have derived that the maximum error for any prime p is 3p minus 5 over p. Okay, so if p is 3, 3 times 3 is 9, minus 5 is 4, divided by 3 is 1 1/3. Okay, so the maximum error for 3 is 1 1/3. If p is 5, then 3 times 5 is 15, minus 5 is 10, divided by 5 is 2, so it's 2. And if e is 7, it's 2 2/7, etc. All right, so the maximum error in my pi sub 2 star of n is given by this equation. E max sub n is the sum of p equals 3 up to the largest prime less than the square root of n of e sub p. And this turns out to be less than 3 pi of the square root of n, where pi is the prime counting function. Okay, the number of primes less than the square root of n. Okay. All right, so that's the maximum error. The next thing I did was I made a plot. So this blue line here is my pi sub 2 star of n, and these red lines here are plus or minus E max. Okay, and this gray line here is the actual number of twin primes less than n. Okay, and you can see that the actual number of twin primes less than n lies comfortably between pi sub 2 star of n plus or minus E max of n. All right, and because this E max of n increases at a very slow rate, the prime counting function of the square root of n, so it's actually increasing at a value less than the square root of n, whereas my pi sub 2 star of n increases with the number of pairs. So this is proportional to n. This is practically linear because w sub n approaches 1. So it's practically linear. And pi sub 2 star of n goes up indefinitely. Okay, so this proves that there are an infinite number of twin primes. All right, so in summary, I derived this pi sub 2 star of n to approximate the actual twin prime counting function. And then I proved based on by induction that pi sub 2 star of n goes up indefinitely because it increases by at least 1 between pi sub 2 star of p sub I squared and pi sub 2 star of p sub I plus 1 squared. And then I proved that the maximum difference between pi sub 2 star of n and pi sub 2 of n, the actual twin prime counting function, is less than 3 pi of the square root of n. Okay? And since 3 pi of the square root of n increases at a much slower rate than pi sub 2 star of n, then there is an infinite number of twin primes. Right? And here are links. Here is a link to the proof of the definitive proof of the twin prime conjecture, and it has all the nitty-gritty details that I did not include in this presentation. Please make sure you're looking at the latest version because the latest version, the earlier versions didn't have the error analysis. Okay, and these are my references. All right, and let's close out with my conjecture, the Watanabe conjecture number 1. This conjecture states that there is at least one twin prime between n squared and n plus 2 quantities squared. Okay, so for example, if n is 2, then there's at least one twin prime between 4 and 16. That's 2 squared and 3 squared. And in this case, there's 3. For n equals 5, there's at least one twin prime between 25 and 49. 5 squared and 7 squared. And in this case, there's 2. There's 29, 31, and 41, 43. So there are some examples. So I'll let you guys come up with a proof of this conjecture. All right. Thank you very much for watching the video, and take care.